Okay, so this is the main thing to remember, is that when you're doing an actual definite integral, the area we're looking for is the integral applied at the second value, or the x is the last one, and minus the value at a. So this was where we started. Then it changed to this. Okay, from a to b, what's the integral? And the way we actually find that is we take the antiderivative of the function, we evaluate it at x, which in this case, our last point is going to be b right here, and subtract the a value. Is that the end? Okay, good. Okay, we're going to try and look at a couple concrete examples before we go. And this might be, do we have this one? I don't know. There's like a weird box shape around something that I don't know why it's there. Okay. So we're finding the area under the curve from 1 to 2, from there to there, right? That's what we want to know. So it looks like it's more than 1 and less than 4, right? Because it's 1 unit wide. On the left side, if this were a box right here, it'd be 1 unit. And if this were a complete rectangle, it would be 4 units. We could maybe think of it like a triangle. So it'd be 1 unit here and then 1 by 3. So like 1.5. I'm thinking out loud here. See, if you draw a little line right here, 1 wide and 3 tall. Well, what's 1 times 3 is 3, and then half of that's 1.5 plus 1. Yeah. That'd be my like geometric estimate. Okay, so let's look at the definite. So this is how we would write that. From 1 to 2, we're going to take the definite integral of x squared, and then dx is with respect to the variable x. So this straight bar is after you have done the integral, but before you substituted in the values. So remember, we add 1 to the exponent, so we get 3. And then we do 1 over 3, so that when I multiply by the 3, I'm left with a coefficient of 1. This straight bar means now I need to integrate it specifically at the value 2, and then subtract the value at 1. So 1/3 of 2 cubed minus 1/3 of 1. So we get 8/3 minus 1/3. This is the area from 0 to 2. So notice how if I just do this, if I just do the ending point, that's the area from the origin all the way to that number. But then this number is this white unshaded part. So I'm taking the whole area minus this starting piece. Okay, so 1/3 would be the area of this white region. 8/3 would be the area of the total region. And if I subtract them, that 7/3 is the area of the green region. And we'd estimate 2.5, and this is what, 2.3 repeating, right? So it's kind of curved underneath that triangular approximation. Okay, get your graphing calculators. Now's the fun. There's two main ways to evaluate integrals on your graphing calculator. All right, so on the graphing calculator, yeah, if we go, I think it's math first, isn't it? Or am I wrong? Look down here. You see anything in this region that looks like it might be the right thing to use? This is in math, the math menu. Anything look like a definite integral? Yeah, function integral. Ooh, so math 9, this is on the TI-84. So if I hit that, it's going to bring, ooh, nice. So the one we were just looking at was from where to where? Which one do I put in the bottom? 1 to 2. And what's my function? There's a lot of murmuring. dx. Enter. And if you're really super lazy, you can hit math into fraction. Oh, I'm so lazy. Which is the 7/3 that we got just a second ago. Whoa. Okay, if you go to math and hit, what is it, 9. Some of them will just bring up parentheses, which is what you have, right? Okay, you're going to enter these 4 things in this order. First, you're going to type x squared, because that's your function. Then you're going to hit comma and hit x. That's the dummy variable. Comma, your first value is 1, comma 2 is your second value, close parentheses, and try it then. Does it do it? Okay. So there's a little different entry there.